Okay, so we're continuing on with chapter 4 for deflection, and with a sort of a side trip to chapter 19, I think. I think in the 11th edition, it still is chapter 19. Where did my book go? Yeah, let me double check on that. This is, chapter 19. So, this is like an introduction to finite element analysis, and it kind of fits in well with what we covered in the last class, which was sort of like this introduction, or maybe not introduction, but review of deflection. So let's take a look and see what we have. Right. So today we're going to talk about deflection part 2, introduction to FEA. I'll talk about the general FEA procedure. Talk a little bit about stiffness matrix formulation, what that means. Talk about the element types and something called the degrees of freedom. And I'll kind of generally talk about computer numerical solutions versus a direct matrix inversion. And then I'm going to demonstrate some SolidWorks FEA using SolidWorks simulation. So here you go. Here is the big picture in terms of what we have. Okay, so we create a model, right? We create a SolidWorks model. Or just think of it an FEA in general. All right, what we're doing is really kind of creating a model of the world, and in terms of how it's attached, what it's made out of, what's the geometry of it, and what the loads are going to be applied onto the thing. And then in FEA, we discretize it, right? So here's the little thing I wrote, the big idea here. We have the model, we discretize it, we figure out what the stiffness is, we put the loads on, we get the deflection. From that deflection, we're able to get the strain. From the strain, we're able to get the stress. So describe it a little bit more. So we're creating a representative geometry, a model, right? And if you're a Monty Python fan, it's only a model, right? Camelot. If you don't know that reference, you need to watch Monty Python's Holy Grail. And we discretize it, right? So I think sometimes I just jokeringly say we're going to make it out of Legos, right? We break the thing into parts. That's the finite part of the thing. Otherwise it would be infinite elements, and those elements are all joined together at the corners by nodes, right? And we'll talk a little bit about what a node is. So using these elements, now the baseline element by the manufacturers of the FEA, the writers of the FEA code, a lot of times we'll call these codes, they put a lot of effort to try to make these categories of different kinds of elements that can, when you mesh them correctly, will do a good job of representing how stiff that part is, right? And so it's based on geometry and material properties, but also there's different kinds of elements. So sometimes there's, in the history of FEA, there's been a lot of work in developing different element types that are useful. So we apply the loads and the constraints, the boundary conditions, right? And a lot of times that's a good source, by the way, of error. Operator error is putting the wrong kinds of constraints to represent how the thing is actually being held in place. Then we solve for the displacements, which are really the unknowns, right? And these are like and they're located at the nodes, right? So that we find the displacements at the nodes, and then we work backwards and we say, okay, if that's the displacement, here's the original shape of the thing, so it has this much strain. So then we divide that really by the elastic modulus, right? Well, no, actually we multiply it by elastic modulus, but more the constitutive equations, as we just saw in the strain gauge problems, that we can find stress from strain. Well, we only did it at one point, but you can calculate in this big matrix and get all the material properties to represent the stress based on Hooke's law, basically. So that's kind of like the big idea. It runs into some problems. So at the heart of FEA is really this equation, and that's just really just force is equal to stiffness times displacement. So And by the way, I want to point out that the name finite element analysis isn't really only applicable to structural things, although that's probably the way most, at least I think, most people associate it with, like making these computer codes. It's actually a method to solve partial differential equations. And the same concept that's being applied with F equals KU can be done with like thermal analysis and even magnetic analysis, and there's all kinds of different things. So you just be aware that it's a big field, and these tools are have a lot of analogous solution strategies underneath the hood. What they're doing, it's not magic. All right, so axial stiffness, I really did this in the last class, but we remember that we have axial stress, axial strain, Hooke's law, and we're able to put those together and come up with the stiffness of the thing. And in axial, that's FL over AE, right? So the stiffness that we have right there is actually AE over L, right? Just as a reminder. I had some other stiffnesses, right? So here's the axial stiffness, but here's a torsional stiffness. We mentioned this again in the last class, where we have the angular displacement is TL over JG, or GJ here in this case. I like the J first. We could create, we call this a stiffness. You do the same thing with a beam. If we know what the deflection is from this relationship right here, we could find what that stiffness is by turning this on the force over the displacement. And notably, this would be like a linear spring, right? But only up to a point. So we have to worry about nonlinear behavior. And FEA, at least in the baseline package that you would get without any advanced solving, will really be restricted to small displacements, right? So large displacements will start to become nonlinear, and that can become more challenging to solve. And we have to solve a nonlinear problem, you need iterations, and that can take a lot of solving power. But also, that's usually a more expensive version of if you're buying your FEA code a la carte, and quite often people do, because they only, companies will do because they don't want to pay for something they don't need. But just be aware that large displacements is one of the nonlinear solving things that has to happen. Another very common nonlinear problem is to have materials that aren't linear, right? Because we're relying on that Hooke's law where we have a linear slope. But if you don't have a linear slope, you have a nonlinear material. And some materials don't have the same properties in all directions, right? So that's also another nonlinear material. Just be aware. So the stiffness matrix, and I think I'm going to call this, and then I'll go into another video because this video will be too long. The stiffness matrix is the big thing that we do. So up here, I said at the heart of this is this equation, F equals K U. I'm using U for displacement. That's just generally what's used when discussing these things. But you see that I put funny little brackets around here, square brackets around the stiffness, and then the funny little, I guess they're called braces, right? Well, this is a column. This is a big square matrix, and this is another column, right? So we want to look at, and that matrix, that stiffness matrix, is the thing that we have to solve, right? So all these elements are connected by nodes, and the simplest thing that you want to start with, the simplest element, is just a simple link, sometimes called a truss. It's just a two-force member. So all it experiences is axial, right? There's nothing else taking place right here. No bending, no rotation, nothing. Well, I guess bending and rotation. Okay. But anyway, it's just a simple link. It's the first one. And the stiffness already is AE over L. So we can take and we can say, well, at this node I right here for this element, we could say that we could find this force is going to cause is going to be found by that stiffness times the difference between the displacement of the position of U at I and U at J. So we have that equation. And then also we could say, well, the force over here can just as equally be stated this way right here. So what we have is, just for a single element, we have two forces. We have a stiffness that kind of relates the two forces and the two displacements right there, right? So there is your first stiffness matrix for a single element. And by the way, the load might be known at one spot and unknown at the other, and we might set the boundary condition at one being 0. So like the unknowns might be the reaction load and the displacement. But in this simple case, you could just solve it by hand. Right? Now, if you had two elements, right? So we're going to join two elements together. So we already have like the element formulation done by the coders was just to set that, for this element right here, we're going to have K, and it's going to equal these things. You notice this is diagonally symmetric, right? That's also something that's that occurs most often. Okay, so we have now two elements. We're going to place these two elements together, and so we can see separately, here's what the two equations would be, right? So here's the element formulation, all right? So here's the stiffness of one and the stiffness of two. And these two things, maybe this part on the left has a different diameter than the part on the right. Could be a different material. That might cause even more problems, but they could have different stiffnesses, just saying. And we merge them together, and you can see now we have a 3x3 stiffness matrix. We have force on the left, right? These are external forces. We have displacements, and we have a stiffness. And you'll note that there's zeros here. Okay, so that's going to start happening a lot. There's going to be lots of zeros on the off diagonal stuff, and it'll still be symmetric down the diagonally symmetric. And that's a very common thing to do. So the real thing that we need to solve for most often is going to be these displacements. In order to do that from a matrix operation, you need to invert this stiffness matrix. You need to take that and by the way, I want to also mention that each of these right here is a degree of freedom, right? So we have 3 degrees of freedom. There's 3 nodes. Each node has a single degree of freedom. That is, that it could either go left or it could go right. That's the only movement that it can make. These aren't 3-dimensional. These aren't even 2-dimensional. Really, just 1-dimensional. Really not going back and forth. So these are 3 nodes. Each has 1 degree of freedom. Therefore, this whole model has 3 degrees of freedom. And so that 3 degrees of freedom generates a 3x3 stiffness matrix. And as we increase the degrees of freedom for the element types and that type of thing, that matrix just keeps getting bigger and bigger. And we could probably solve this 3 degree of freedom by hand if we wanted to, because we could, if we had to, invert a 3x3 matrix. We don't want to, but we could do it. I don't think we'd really necessarily an everyday task to invert a 4x4 matrix, right? And anything greater than that, you really need MATLAB or some type of computer software. But this is the big computational task that computers have to do, and really kind of stymied being able to solve large models was how many degrees of freedom there were and the necessity to invert a matrix, which was computationally difficult. So I'm going to go to a new video here in the next one. So I'm going to be done with this because we already got at the 14-minute point.